All right. Good morning, folks. Let's go ahead and let's get started. I'm going to finish up with the chapter 13 today. And like I mentioned to you yesterday, I apologize for the confusion, but I want to go ahead and finish up with the material from chapter 13 today. And then on Monday, we will do the FET lab. I'll post the two FET labs today after school. And then you can go ahead. You don't have to do them over the weekend, but please take a look at them and then we'll do them on Monday. So on Monday, then we won't have a lecture. You'll spend that time working on the FET lab, and then Tuesday of next week we'll go ahead and we will go over the FET labs. That will give me an opportunity to introduce to you and to the labs, the gas laws. And so, we'll talk about that. I'll quickly review for you gases, and then we'll dive right into the gas laws. Okay. And so I think we should be able to get done with the gas laws by Friday of next week. We'll see how things go. But hopefully we'll get that done in the following week. Then we'll meet, we'll review for the exam. And so the exam, the next exam will be on the chapter 13 to 14 material. Okay. All right, so let's go ahead and let's get started. What I'd like you to do then is let's take a look at number 10. This is the last question from the chapter 13 problem set. Okay? I'm sorry, this is number 10, the last question from number 10. This is from the chapter 13 problem set. Let's take about a couple minutes, folks, and let's start out this morning by answering this question here. That will give us an opportunity to talk about the solids and review solids and where we left off with yesterday, and this property of solids known as melting point. Okay, so a couple minutes, write down your answer, and then we'll get back together and we'll talk about it. Okay. All right, folks. So hopefully you had a chance to answer this question. Again, I think it's a pretty straightforward question that allows us then to address the connection between macroscopic, what we can observe, and what's happening on the microscopic level. Okay. So here we are talking about melting point. Melting point is an intensive property of different solids. Now remember, we talked about boiling points as being an intensive property of different liquids. So different liquids have different boiling points based upon the interactions of the particles with each other, okay? And that's going to depend on the nature of those molecules and those atoms. Melting point here is unique to different solids. So different solids will have different melting points for the exact same reason. The particles that of a particular solid will interact with each other differently, okay, than another solid. Okay? So different solids, based on their interactions, based on the attractions and interactions of the molecules and atoms that make up that particular solid, will determine then the melting point of a solid. Okay? All right. So first of all, let's go ahead then and let's describe what we see. So let's describe the macroscopic, what's happening at the macroscopic level with the melting point. Okay, so here's our solid. Let's just pretend that there's our solid. Okay, and our solid then, remember we talked about solids, they have definite shape and definite volume. Okay, so here's our solid, definite shape and definite volume. And the reason why this solid has definite shape and definite volume is because the particles then are packed real close together. Okay, the particles are packed real close together in a three-dimensional structure. Okay? And because they're packed really closely together, there's very little, the way these particles, the way they move is going to be very different from the way then the particles of a liquid or a solid moves. We said then that the way that these particles move is that they move in a rotational and vibrational manner. That means they kind of sit in place and they fidget. Okay, so all of these particles, they will move, but they will move in a lateral rotational manner. And so I draw these arrows here to represent them that they, as they move through an equilibrium point. That means then they move left. Let's say, for example, they move left, then they'll come back to their starting position, then shift to the right and come back to their starting position. Same thing along the y-axis as well. Okay. So that's the nature of the motion. So they have a vibrational and rotational motion about them. Okay? But they do move, and they do move, and as they move, they will move with a certain amount of kinetic energy, and they will move, and that kinetic energy will depend on the temperature that the solid is at. Okay, so so the solid here exists at, and we'll call this temperature 1. Okay, so the initial temperature. So temperature 1, we have then the solid particles moving. Okay, we have the solid here. It exists in the solid state. Okay, all right. So what happens then? We start to increase the temperature. So as we increase the temperature, so we're going to increase the temperature. Now, what does that mean then? As we increase temperature, we are going to increase the heat energy. Okay? So a measure of the heat energy then is temperature. So as you increase the temperature, what you're doing is you're increasing the amount of heat energy. As you increase the amount of heat energy, you can imagine then what happens to these particles. Okay, as you start to increase the heat energy, you can imagine these particles start to move faster and faster. And I purposely, hopefully you recognize this, I purposely have drawn these arrows to be longer, meaning then that they are moving faster. They are still vibrating, they are still rotating, but they are doing so at a much faster rate. At a given point, you can imagine that at some point, as you continue to increase the temperature, that means you continue to add heat. These particles then will continue to increase their kinetic energy. They will increase their kinetic energy, and at some point they will be moving so fast they're going to slip, and they're going to start moving in a translational manner. Okay? And at that point, then, when they start moving in a translational manner, they start to, and again, that's what separates the liquids from the solids, the way that they move. At some point, when they start moving in this translational manner, okay, you have then particles that will become liquid particles. And so they will move in a translational manner. That means that, remember, they're moving from point A to point B. They're changing their position. So the nature of the motion here, again, here we have 4 arrows. The nature of the motion here is that they move in a single direction, okay, random, rapid, constant manner, okay? But this is a random manner here. So they're moving in a random manner all around, okay, but they are moving in a translational way. So here we have 4 arrows representing motion around an equilibrium point. That means rotational, vibrational motion. This is going to be translational motion. And this type of, and so what happens here is that at this point here, the compound or the substance is at a new temperature. Okay, so this is going to be at a higher temperature. So let's make sure you keep this in mind, that the temperature in which the solid exists at is going to be lower than the temperature in which the liquid exists at, which means then the kinetic energy of the solid is going to be less than the kinetic energy of the liquid. Okay, and so you want to make sure you keep this in mind as we go through this. Okay, that at the melting point then, okay, at the melting point then, you reach the point where these particles here move just fast enough where they start to do this. They start to break up into, and they start moving in a translational manner. Okay, so that's what we see happening when solid melts. So we see this. So we see the solid becoming a pool of liquid here. But what we don't see is the nature of that motion. Okay, the movement from rotational and vibrational motion to a translational motion. That is what specifies, and that's what makes, that is the difference between the liquid and the solid, okay? All right, so hopefully make sure you write that down, okay? And maybe I'll just write it here. So at the molecular level, at the macroscopic level, we're going from rotational slash vibrational motion. We're moving from vibrational motion. This is on the solid side, and we're moving to translational motion on the liquid side. Okay. All right. So there it is. We've described then the what happens to a solid when it gets to the melting point on a macroscopic level. So let's go ahead and highlight that. So this is the macroscopic. Okay, that's what we see here, solid becoming a liquid, and the microscopic here as well. Okay, so rotational to vibrational motion. And we've also described it on a macro and microscopic level here in terms of its temperature. So that's the macro. We can observe the temperature change. We can measure that. And this is the micro right here. Okay, kinetic energy of the solid is going to be less than the kinetic energy of liquid. We're increasing the kinetic energy of those particles. Okay. All right, very good, folks. So diagram this if you have to, but like I said, that's make sure you're able to explain that. Okay. All right, so we're talking about phase changes here, folks. And so the question is asked, I asked you to answer was about a phase change. Let's finish up this chapter by talking about these phase changes here. Now, most of us are familiar with a phase change. A phase change is simply a change in the state of a particular compound. Okay, so let's say, for example, what we just talked about here, we talked about the change from a liquid, from a solid to a liquid. So we're moving in that direction there. The solid becomes the liquid. We refer to that as melting. And so we know what melting is because melting, we use that quite a bit. That refers to the change in state of a solid to the liquid. Okay. On the opposite direction, then, if we take the liquid and we make it a solid, we refer to that as freezing. Okay. So these phase changes, what we want to be able to do is we want to be able to describe these phase changes on both the macroscopic and the microscopic level. What causes it, okay, and then how we can describe it. Okay. All right. So with that said, then there are a few others. We talked about vaporization here, and so we are not talking specifically about evaporation or boiling, but we're talking about the change in state from the liquid to a gas. That's what we refer to as vaporization. And then in the reverse direction, when we take the gas and we cool it and then we bring it back down to the liquid state, that is going to be what we refer to as condensation. Okay. However, so those types of those phase changes, those four that I just mentioned there for you, we are familiar with. That we see on a daily basis for the most part, and we experience those phase changes. Okay. The two phase changes that we come across less frequently are the phase changes between the solid and the gas, and the gas back to the solid. We're so used to imagine or thinking or seeing then that in order to get to the gas state, we have to melt the solid first and then vaporize a liquid to get to the gas state. No, we can actually get directly from the gas state. So if we go in this direction, we can get we can get the solid to vaporize directly right into the gas. That process is what we refer to as sublimation. This we may have, some of us may have experienced a little bit, especially if we have used dry ice before. If you've used dry ice before, you've seen solids sublimate. Okay, so I'm sorry, let me go ahead and clean that up a little bit. Okay, so we have seen this happen, especially, like I said, for those of you folks who have experienced or have had some experience with dry ice, which is solid carbon dioxide. You've experienced sublimation. You've experienced the solid go directly into the gas state, and so we'll talk about that in just a moment. But I would wager that probably none of us, and if there is any one of us who have experienced this next phase change, I would be very impressed by that. And that is then the gas going directly back to the solid state. So the gas, instead of condensing, it goes directly to the solid. We refer to that process as deposition. Okay? And that actually requires not only a drop in temperature, but an increase in pressure as well in order to get that done. And so that's why I was saying, if any one of us has ever experienced that before, then I would be fairly surprised, and I would be wondering what you're doing on your free time. Okay. All right. So, but those are the phase changes, folks. So we have a total of 6 phase changes in all. And I want to talk about those 6 phase changes and how we carry them out, and then also what we do to, and then I'll talk about sublimation a little bit right now. Okay. All right. Very good. So let's go ahead then, and let's talk about sublimation a little bit. Okay. So sublimation is the phase change that takes us directly from a solid to a gas. And what I have pictured for you here is carbon dioxide. Okay, solid carbon dioxide, which you can buy at the store as dry ice. Okay, and so what happens here is that solid then vaporizes. The solid then goes directly into the gaseous state. Okay, and just like with liquids, then okay, we can describe then this sublimation point in a very similar way that we can describe the boiling point. Okay, and so with the sublimation, then remember. With evaporation, remember, we saw then that the particles that evaporated were the particles at the surface of the liquid. Well, with sublimation, the same thing happens. It's the particles at the surface of the solid that starts then to gain enough kinetic energy where they break their attractions with the particles around them, okay, and then they leave with a certain amount of kinetic energy. Okay, so they leave with a certain amount of kinetic energy, and because they've absorbed that energy, and so they leave and they become the gaseous state. Okay, so the same way that we can describe evaporation for liquids, we can describe sublimation for solids. Okay, but just like with liquids, also, okay, as these particles leave with their kinetic energy, they start to the number of gas particles start to build up above the liquid, and so they also exert a vapor pressure. So therefore, when solids sublimate, when solids sublimate, they will exert a vapor pressure. Now, in theory, almost every solid should be able to sublimate. If we change the temperature, if we alter the pressure and alter the temperature of its surroundings enough, we should be able to get any solid to sublimate. Whether that actually happens in practice, that's a different matter, because it becomes very difficult in order to get other solids to sublimate. Okay? All right, the carbon dioxide sublimates fairly easily and at room temperature. Okay? All right. So with that said, then I want to leave sublimation as that. Okay, we won't discuss that much more, but just make sure you're aware of it. Okay, what I would like to do to finish out then is I want to talk about these phase diagrams here, because what these phase diagrams allow us to do is they allow us to determine the conditions at which these phase changes occur. Okay, so a phase diagram is basically a graph. It is a graph, okay, that plots, if you notice here, pressure along the y. So we have pressure along the y and temperature along the x-axis. Okay? So we have pressure along the y, temperature along the x-axis, and then what we do then is we, at each point along the this graph here, we can plot the temperature and pressure at which a liquid can exist. Okay, so we can imagine different points here that a liquid can exist. So at this particular point here, for example, this point here represents a coordinate in which you have a temperature along the x as an x coordinate and pressure along the y as a y coordinate. Okay, so each point here will have a temperature and pressure associated with it. So on a phase diagram, we can plot different points on this phase diagram, and each point then represents a temperature and a pressure as a coordinate. Okay, and so each point here that I've highlighted for you has a temperature and a pressure associated with it. Okay, all right. So I'm sorry, I wanted to do this one closer to this point here. Okay, so let's go ahead then. And so if we can examine this point here, okay, so at this point here, so this point lies right along this line here. So this point here has a temperature associated with it, and we trace the line down, and it's 100 degrees Celsius. So it's 100 degrees. At this point here, the substance is 100 degrees, and then we trace it over to the y-axis, and the y-coordinate is 1 atmosphere. Okay, so the coordinates for this particular point then is 100 degrees, 1 atmosphere. Okay, and so we can do the same thing for any of these points. So let's go ahead and let's try this one right here. So at this point here, okay, we trace up. The temperature here is about 0.01 degrees, and the pressure is 0.006 atmospheres, okay, ATM. Okay, so any point along this graph here. So let's say I chose this point here. Let's trace the lines again. Okay, so let's go ahead and trace the arrows. At this point here, the temperature, let's go ahead and trace it down right there. And we're gonna have to estimate the temperature right there. Okay, so and the pressure would be right around there. Okay, so the coordinates for this point then, if we wanted to write that in, the coordinates for this point then would be what? Negative, and so this is below 0, negative 15 degrees Celsius, and the pressure here at this point then is going to be less than 1, so we'll say that about 0.9 atmospheres. Okay. All right, so at every point on this graph here, there is a temperature and a pressure associated with it. Okay, so what we can do is each point here gives us the relationship between liquids and the temperature and pressure for a particular compound. Okay. All right, so let's take a look what else it gives us. So that we already have. Okay. So at each one of these points here, so what we have here also is we have 3 lines. So we have 3 lines, and all phase diagrams have 3 lines. Okay, and we have a line here, we have a line here, and a third line here. You notice that for the first phase diagram. For the second phase diagram, same thing. We have a line here, we have a line here, and we have a line here. And what you notice here with the phase diagram then is that each line separates a region of space. on the graph here. Okay, and so let's take a look at this line first, right here. This line first. Okay, this line here seems to separate the solid. On the left hand side of the line, we have the solid. On the right hand side of the line, we have the liquid. Okay, and so we have for this line going straight up, we have that. So looking at this here, this line right here, the line that goes straight up, then if we take a look at it, it separates the solid, and here this is ice, this is solid water from the liquid water here. So this line right here separates the solid from the liquid state. Okay? Let's take a look at this line right here, this curve that kind of curves up and towards the right here. If you notice that this line right here separates the liquid, and so to the left and up and to the left, you have the liquids. We have this side here that's shaded in the liquid, and below that we have the gas. Okay, so this line seems to appears to separate out the liquids from the gas. Okay, and then this third line right down here separates then the solids from the gases. If you notice here, if you go to this third line here, it separates out the solids from the gases, and we see that happening here as well for water. Okay, so this line here, this curve here separates out separates the water in the liquid state from water in the vapor state here, which is the gaseous water. Okay, and then this line right here separates the region of the graph that we refer to the solid from the gaseous state. And so those are the key characteristics that you need to make sure you keep in mind as we move forward. I'm running out of time. I've ran out of time here, but what I'd like to do on Tuesdays is take a little bit of the time to finish up these phase diagrams. But what you can notice then is that there are essential components of a phase diagram. First of all, you have then the pressure. What you should recognize is that it's a graph that has pressure along the y, temperature along the x. Okay? So those two key components of the graph you need of phase diagram you need to remember. Secondly, then you need to remember that every point on the graph here, represents a temperature and a pressure. Okay, so that's a third key component of the phase diagram that you need to remember. Fourth, you need to make sure you keep in mind that there are 3 lines that will appear on any phase diagram, and each line then separates out the different states of matter. Okay, and so those are the 5 key components we need to be able to understand that about the phase diagram. And so what we need to be able to do is we're going to be able to interpret these phase diagrams not only in terms of these 5 key components, but what they mean in terms of how a phase change will occur. That is the temperature and the pressures that we have to achieve in order to achieve a phase change. So that's why these graphs are called phase diagrams, and that is where I want to pick up with on Tuesday when we meet again. Monday, remember, there won't be a lecture. You'll work on your labs, okay, and then you'll submit that. I'll give you the instructions on Google Classroom, so please make sure you finish the lab and submit it. Very much like you submit your homework and these lectures here, submit it, and then you'll be done with it, and hopefully you'll get it done within the class period. If not, I'll let me know. I'll probably extend the due date till the time that it's due to 11:59 on Monday, but make sure you get it done. Okay. All right, folks. Very good. I'll see you next on Tuesday of next week. Okay. All right. Have a good day, and I will see you on Tuesday.